Let's talk about the Jak-Stat pathway. This particular hypothetical cell is showing side by side different receptors. As you can see, the intracellular signaling is rather complex, but when we look at the Jak-Stat signaling pathway, it is relatively simpler than the others, using basically the genus kinases for activating the stats going into the gene transcription. The relative simplicity of this intracellular pathway has opened the door for many different therapeutic modalities inhibiting these Jak-Stat pathways in different ways. There are four genus kinases. They are called Jak1, Jak2, Jak3, and TYK2. And they signal through any one of a pair of seven STAT members, which are the signal transduction and activator of transcription. These are factors that actually, once they are activated by the Jak pair, they translocate to the gene and they activate the gene transcription. The different cytokines will express the receptors that have associated the genus kinase pair within the intracellular domain. The Jak3 is very specific to the white blood cell lineage, and it can only be associated with Jak1. There's a need for two JAKs to be able to transmit a signal. The other three JAKs, Jak1, Jak2, and TYK2, can actually be associated with any one other for a pair in the different receptors. What you see on the right, the second to the last, is three JAKs, all three except for Jak3, as I mentioned, which is very specifically only associated with Jak1. But what you see here, Jak1, Jak2, and TYK2, can actually associate in a pair with any one of the other JAKs as a pair. Is not a triad, is a pair. And there is a series of cytokines that can use in their receptors either a Jak1 or Jak2, Jak1 or TYK2, or Jak2 and TYK2 to produce a signal. This evidently is a reflection of how important these pathways are in life. When you have a potential of using more combinations to be able to produce a signal. On the very far right, you see the only case so far that I know that uses two JAKs of the same. In the other circumstances, it's always two different JAKs in pairs. But in the case of the far right, we have Jak2 associated with Jak2, and this is very typical of growth factors, not cytokine receptors. This is a table that's extracted from the publication listed below. And just bear in mind, I will explain to you how to read this table. But for more accurate information, I am taping this video in 2019, but this is a very active field of research. So there's been a lot of different laboratories researching on this, and I wouldn't be surprised if you actually see differences or updates where there might be other signaling pathways or cytokines identified as signaling differently in this Jak-Stat pathway. So the way to read this table is on the first column, we have which one would be the stat that is activated for the different rows. And then you see the columns 2 to 5 are the four JAKs and how they are used. In the rows, I have put the different cytokines. So when we see the very typical adaptive immunity system will signal, as I mentioned, using Jak3. Jak3 can only associate with Jak1. So these 6 cytokines are cytokines that will bind receptors that are very specific for the white blood cell lineage. So an inhibitor potentially that can inhibit JAK3 signaling, even if it does not inhibit JAK1, would be successfully inhibiting signaling by any one or all of these 6 different cytokines and would be a control of adaptive immunity. Outside the adaptive immune system, there are many different cytokines that have to do with cell differentiation and cell function, and they're not necessarily restricted to the white blood cell lineage. So, just as an example, interleukin 4, for instance, which is one of the JAK3 dependent cytokine signaling pathways, IL-4 is the cytokine that triggers T cell differentiation into a Th2 phenotype. For more on Th phenotypes, there are several other videos, including a video in my channel with more updated pathways on how the T helper cells differentiate. Interleukin 21 is going to be differentiating the naive T cell into a Th17, same as interleukin 23. And interleukin 12 is the key cytokine that differentiates into Th1, same as interferon gamma. So what we see here is that within the JAK3 dependent, we have at least 2 cytokines that would produce differentiation to 2 different phenotypes, Th2 and Th17. So with a JAK3 inhibitor, those 2 could be modulated. Whereas for the pathway differentiation using IL-23 or IL-12, which differentiates into Th1, now we have the other 2 JAKs in combination. So when we look at our hypothetical inhibitor of JAK3, that particular drug would not be able to modulate or inhibit a Th1 differentiation mediated by interleukin 12 because JAK2 and TYK2 would still be available for signaling and activation. So in this case, we would need to have a drug that not only inhibits JAK3, but let's say that this drug can also inhibit TYK2 signaling. So in this case, the control for these cytokines that may be driving the majority of the Th phenotypes could be theoretically controlled. Now, I did mention interferon. So, interferon gamma is another driver of the Th1 differentiation. And with the example that I had just been talking about, an inhibitor of JAK3 and TYK2 would actually allow interferon still to signal. So, there wouldn't be a complete control of Th1 differentiation and signaling that interferon gamma is not only doing that differentiation. Interferon gamma is a very important mediator of inflammatory responses and also innate responses. So we would have to have another control for innate immunity. And as you can see here, innate immunity also is the one that uses, not surprisingly, because it's very important for life, it is using a combination of more than 3 potential JAKs, JAK1, JAK2, or TYK2. So having again an inhibitor that only inhibits JAK3 and TYK2 would not completely control all of the innate and adaptive immune responses. So in this case, when we have a combination of any one of these other 3, for instance, take interleukin 6, we would need to have now a drug that inhibits not just the JAK3, but also the JAK1 and the TYK2. So now we could control several different responses. And the reason why I'm explaining inhibition of JAK3, inhibition of JAK1, inhibition of TYK2, just remember this would be in a single drug. You don't have to give the patient 3 drugs, but they could have different affinities to the different JAKs. But the most important thing is, as I had mentioned, the growth factors use JAK2 and JAK2 in combination. So sparing the inhibition of JAK2 is an important condition when you look at the JAK inhibitors that you have in your armamentarium for therapeutic drugs. Just understand if that particular inhibitor produces inhibition of JAK2 and to which concentration it does it. Because what you want to try to avoid is inhibition of epoetin or thrombopoietin or CSF that could produce anemia, thrombocytopenia, or infections. So you want to try to see that your inhibitor that you're using understand how much it inhibits JAK1, TYK2, JAK3, and if it does inhibit JAK2, to which dose? How does it translate in terms of the dosing so that this could be spared? In the pharmaceutical world, this has been a key feature for developing JAK inhibitors that could spare inhibition of JAK2 while inhibiting JAK1, JAK3, and or TYK2 in different concentrations. So let me just walk you through a publication by Meyer, which I'm listing there. And it does explain a bit on how different inhibitors, different drugs penetrate the cells and could produce different degrees of inhibition. So let me explain to you in brief how these experiments have been conceived. You have a solid phase in the laboratory, and you have, for instance, a T cell. This T cell will actually respond to IL-15, which is one of the first 6 cytokines that uses the JAK3 JAK1 pair. What the T cell does after the IL-15 engages the receptor is that it becomes activated, and this activation can be measured in this setting. When using monocytes, for instance, we can now look at the growth factors. And likewise, when the growth factor is spiked on the plate that has monocytes, these monocytes will respond because they do bear the receptor. So this signal in the presence of the stimulant in vitro will produce, for instance, in this graph, when we look at the red dots or the purple or pinkish squares, gives us the 100% stimulation. So now we add a putative inhibitor, which is a small molecule, on the plate. When we add it on the plate before spiking with the cytokine, in different concentrations as shown here on the x-axis, we have a logarithmic scale based 10 of concentration. So it's very, very highly concentrated as we go to the right. And what's going to happen is that if this particular small molecule successfully inhibits that binding, then, or the activation driven by interleukin 15 in T cells or GM-CSF in monocytes, there's actually no signal, or the signal is reduced as shown in the y-axis. So as we move to the right, there's less and less of the activation, which is the percent inhibition. I hope that you're with me so far. This is the way to read this kind of experiment. The way that this experiment is translated in publications, as the one I'm quoting by Meyer in the bottom, is that you see the same graph I had shown before. So let's take interleukin 15. When you look at the 50% inhibition on the y-axis, you draw down what was the concentration of your drug that produced that 50% inhibition. And bear in mind, this is a logarithmic scale. So what you see on the table is that on the substrate of CD8 positive T cells, interleukin 15 signaling via the JAK1/3 using STAT5 will require 56 nanomolar concentration of this particular drug to inhibit 50% this signaling compared to when the cell has absolutely no inhibitor, so 56 nanomolar. When we look at the GM-CSF, which is a growth factor that requires JAK2 and JAK2 on monocytes, the 50% inhibition now requires 1,377 nanomolar. A significantly higher amount would actually inhibit this JAK2-JAK2 pathway. So this particular example will show you that when you talk about a JAK inhibitor, it all depends on the dose. So the important thing is to know in humans what is the dose that would translate to these cell assays, and am I actually using uh, a dose that's small enough that can inhibit the inflammatory and autoimmune pathways that are activated in disease and sparing the JAK2, JAK2. So using this kind of table, the same publication presents a very comprehensive result on this particular drug. The Meyer publication goes on to explain how this particular drug inhibits the different cytokine signalings using different cell substrates. So as an example we saw from the previous image is that you would actually need about 25-fold higher exposure or dose to inhibit the JAK2 pathway compared to the JAK1/3 signaling by IL-15. Now you can see in this table that for the IL-21 you even need less amount of the drug to inhibit that particular pathway. So it depends on which cytokine you're looking at. But if you looked at the average for IL-15, it's 25 times higher concentration to inhibit growth factors. And if you move down on the table, you now can have different cells that will be responding to different cytokines using different stats. But if we use the example, for instance, of the interleukin 6 signaling via the STAT3 for monocytes, that you have about 400 nanomolar. So that's about 6 to 7-fold higher than the 56 nanomolar, but it's still way below the level that you need to inhibit the JAK2 pathway. From this publication, Meyer and Goreschke publication, this particular drug was actually concluded to be a potent inhibitor of JAK1 and JAK3 and potentially reduced cellular potency for the JAK2. And this is one of the drugs that is now available on the market. This is the way I hope that you can now understand how to read this particular publications and understand what is the difference between the JAKs. So one question that comes to everybody's mind as the future of therapeutics for rheumatic diseases, inflammatory diseases um, of the gut, and also on the skin, we're seeing more and more JAK inhibitors. Is one JAK inhibitor the same as the other? And the answer to this question is no. They have different characteristics. A publication that I found on different characteristics. This publication from 2014 is just one example of a comparison between available different inhibitors of JAK. And as I mentioned, I really urge you to look at recent literature. There's more and more JAK inhibitors in the market. So for you not to get very confused, I'm hoping this is going to help you understand that different JAK inhibitors have different characteristics. And this is a side-by-side characteristics on one laboratory that tested them side by side. And you can see just by looking at the numbers in the different rows of the nanomolar concentration needed to inhibit different cytokines using different JAK pairs and different stats is that the answer is no. One JAK inhibitor is not the same as the other. They have different features, and different diseases would actually require different inhibitor pathways. So keep an eye on JAK inhibition. This is going to be more and more specific for different diseases, especially as we understand better which kind of cytokines, which kind of JAKs, and which kind of stats we would need to modulate with these inhibitors. You will have a potential for actually selecting and choosing the one that best fits the disease and the patient in terms of the pattern and the way that they inhibit the different JAKs and the different STAT pathways. I hope this was useful, and I hope this helps you understand a bit more a field that's extremely active in the research area for new drugs to control autoimmune and inflammatory diseases. As mentioned, these are the references I used. I'll put them in the description below. And I hope you can also tune in other of my videos in the YouTube channel that explain other aspects of immune system, cytokine signaling, and different responses. Thank you.